All right, so hi everyone. My name is Silvin Willemsen, and today I'll be talking to you about some challenges in real-time physical modeling that I've encountered over the last few years. So I started my physical modeling endeavors, I guess, during my PhD at Aalborg University in Copenhagen, where this was one of the projects that I did there, which I wanted to show you as an example for a physical model. There should be sound, but let's see if that... There's enough sound in this presentation, so we can move towards that. Anyway, bunch of strings connected to a plate and bowed with a few bows. Then fast forward a few years. Now I've been working for Baby Audio for a little while. And earlier this year, we released Atoms, which is a physical modeling synthesizer. And that sounds, hopefully, like this. No sound yet? You can come to me after the talk and I'll show you some of these sounds. Anyway, so let's get back to the basics and on the same page, and let's see what physical modeling actually is. So usually with physical modeling, we're looking at kind of dynamics of real-life systems, and these can usually be described by equations, such as this one, partial differential equations. And in this case, it's a one-dimensional system, but we can extend that to 2 dimensions and connect these systems. And the main challenge here is to implement this in, well, hopefully real time, but implement these continuous physical equations into your computer. And some examples of what you can do with this physical modeling is on the one end of the spectrum, you can make very realistic simulations of real-life instruments. For example, audio modeling does that very well with the Swan violin. It's a very nice sound, isn't it? It sounds very realistic. So Swan does a very, very great job at doing realistic musical instruments. But on the other end of the spectrum, we have physical audio. So Modus is a plugin that they made where we have different physically modeled components and configurations that are physically impossible to do. You can find Modus online and hear the sounds for yourself, I guess. Yeah, anyway, so that's on the other end of the spectrum, where we do physically impossible things while still retaining the organic physicality of the thing. And with Atoms, we try to do both, or be somewhere in between, where we have both, well, very physically modeled string sounds, where at the other end of the spectrum, we can also do very weird and otherworldly sounds, I would say. All right. So then why would we do physical modeling apart from this? And a lot of software musical instruments or synthesizers are based on samples. So say that you want to model a violin. And we can change the various input parameters as a player. For example, the bow velocity, the position of the bow along the string, or the bow force, for example. And these are only 3 of the many input parameters that we have in order to play the violin. But you can see how this, if we want to sample all of these different combinations, it can you will use a lot of data and you use a lot of time to sample this complete thing. So with physical modeling, while you're playing, you're changing the coefficients in real time to generate the sound on the spot rather than having to sample everything. But we can also go beyond what is physically possible, as we saw with Modus earlier. We can, for example, change the density of the string. We can change the damping of the string coefficients. And maybe also the radius of the string. So then how would we go about physically modeling this? They're usually in any physical instrument, we can divide it into a resonator component and an exciter component. So the resonator is usually assumed to be a linear system and the exciter nonlinear. Where here the linear system, or the resonator, is what I will focus on this talk, as that has the most computations, like the most CPU heavy part of the algorithm is there. So yeah, that will be most interesting for ADC. So there's various ways that we can model the resonator. In the case of the string, we have a choice of, for example, digital waveguides, which have been around since the 60s, very fast algorithm. We can decompose the string into its modes of vibration, add these modes together, and get a nice string movement there. Or we can use finite difference methods, where we subdivide the string into a grid in space and also stepping in time. And this is what I will focus on in this talk, because it's easiest to explain and I have most experience with that as well. All right, so for the rest of this talk, I will go through some challenges in physical modeling, as the title of the talk suggests. I have 5 for you, and the first one is to actually implement these physical equations that we saw before into discrete time. So yeah, we saw this partial differential equation. This is the one-dimensional wave equation. And if we want to implement that digitally with finite differences, we do this subdivision into grid points in space and stepping in time. And out comes this finite difference scheme that we can implement in, well, any programming language. For example, here we have some MATLAB code where we we loop over the grid in space. And once we're done with this entire space loop, we increment the time step. And so we have a nested for loop there. And in math, this is an update equation or a recursion. And there's a very good reason I'm showing MATLAB code at ADC and not C++. This is because to start off with these physical models, it's a very good idea to start off with a non-real-time programming language. So we can, for example, do debugging and plotting very easily in MATLAB and Python, for example. And there's another reason, which is your general health and sanity. Because, and this is in a very literal sense, because these physical models, when for a slight wrong choice of parameters, they can blow up on you. And they can become unstable. And if you do this in JUCE, your headphones and, more importantly, your ears are not going to be very happy with this. So yeah, only then go to C++ and JUCE. So yeah, that is prototyping before going real-time. All right, so the second challenge, and this is a big one because physical modeling is kind of infamous for using a lot of CPU, right? So we want to run these simulations at audio rate. So if we're lucky, only 44,100 times a second, we need to do several things. And the first thing we need to do is to calculate the entire system. So say we have a string here, maybe 30 points, or n points to be more general. Every single sample, we need to calculate these n different points. We need to update the system. And the way that this usually looks when you write it down is something of the form of this. So we have u, which is the string state, at the next time step is dependent on u at the current time step, some state that we know, and its neighbors. So that's how you get this nice wave propagation, and u at the previous time step. Sometimes you will need more neighbors depending on what kind of model you're using. So you can see how the computations can shoot up here, especially because we're doing this so many times a second. So we're using these states that we know. We're using them as variables and we're multiplying them with some coefficients. And these coefficients, they include the physical parameters. So things like tension, density, cross-sectional area. And we can see that we have a lot of multiplications, powers, divisions here. But if our parameters do not change over the course of a longer time of the simulation, we can pre-calculate these. And we can relieve some of these calculations from the guts of the algorithm. So yeah, we're ending up with some coefficients here that we multiply on these grid points, these variables. And some other thing we can do is to group the terms. So usually the coefficient that we're multiplying our left grid point with is the same as the right grid point. So we can save another multiplication there. Another thing that we have to do so many times a second is to update the system state. So whatever we just calculated, this un+1, in this iteration, will become the current time step at the next iteration. So we're kind of moving all this data up in time so that we can use it for calculating the next step. And for this, it's very good to use a pointer switch. And for many of you here, this might be trivial, but I still want to touch upon that. So usually in MATLAB, C++, whatever, we save these states of our system in some vectors or arrays. And the naive way of updating these arrays from the next to the current to the previous time step is to copy all the state over to the next vector. And if you have n grid points, this is going to be 2n operations, where this guy is going to be overwritten in the next iteration. So this would be the naive way of implementing it. What we can also do is to have a big container and have some pointers pointing to the various like u next, u current, and u previous, and just do a simple pointer switch. And it doesn't matter how long your string is or how big your plates are. This is always going to be only four operations to do a switch with three pointers. And then here, this guy will be overwritten. So yeah, the pointer switch is important, and for a simple string model of 30 points, this is not going to make a big impact on your CPU, but especially if you have bigger systems like this with plates and getting into thousands of grid points, this is really going to help your CPU. Yeah, so as a final tip, implement a limiter or a soft clipper before you do anything else, because again, things might explode and you won't be happy. Mistakes are made. Yeah. So right, we have our working physical model in real time, and now we want to add some parameter control. So we want to change the parameters of the physical model in real time. And usually what happens is that the parameters or the knobs of your plugin are going to be coupled to physical parameters of the model. So for atoms, for example, we have a few parameters that are linked to some damping coefficients. We have the vibrato literally linked to the tension of the string, some density and some weird nonlinear stuff happening. So there's a lot of stuff that is linked to the actual physical model. But yeah, this can lead to problems. And just as an illustration of this, we can, for example, change the density of the string very fast over the course of only 2 samples. Because we are calculating this U at the next time step based on the current state, these finite difference schemes especially, they are made for static parameters. So they're not made for time-varying parameters, which might cause an explosion in the end if you're changing them too fast. But usually, what helps is to change the parameters slowly. If you do it slowly enough, it will be fine. And of course, you need to experiment a lot before you give it to the users to make sure that it doesn't explode. But JUCE has a very nice class, smooth value, that can help you with this. A worse thing that can happen is that you update the parameters while you're doing this calculation in one time step. So we can see here that like while we're in our grid calculation, then we suddenly change something. So the left neighbor might have a different coefficient than the right. And this is what those schemes are really not based on or not working with. So update the coefficient only outside of the scheme calculation, or to save more CPU if there's a lot of computations that need to happen to recalculate these coefficients. You can even choose to do this calculation outside of the buffer. All right, so the fourth challenge, now we have our interactive physical model in real time. We now need to make it sound good. And unfortunately, I don't think you will be able to hear this. Nope. But luckily, it sounds horrible, so you don't have to worry about that. So yeah, the first thing that we usually do when developing physical models is to add damping to the system. And this will already make it, sound less horrible. And also, we can add a little reverb. That also helps. It's a bit of cheating, but it really helps to place it into context. So yeah, a second thing is that parameters really influence each other. So for example, in the case of atoms, like now I'm going to show you a video with no sound, but we can change the damping. We can change the damping up. But what you would have heard is that we're bowing the system. We're getting another overtone. So it goes from, say, a C to the C octave above. And this is what would happen in the physical world as well, where we change the damping of the system, it suddenly goes into another overtone. Yeah, so that is something to keep in mind when developing physical models. So yeah, a real instrument can be really tough to get right in general, and parameter tuning can be as time-consuming as actually implementing the model, if not worse. So some general tips here is to have a nonlinear exciter, first of all. So what I mentioned before, like the bow on the string, that can really create some organic feel to the sound. Also maybe use velocity rather than absolute position. What we usually do is to take one point along the string and like follow its displacement and put that to the output. But sometimes it could help to use the rate of change of that point. And it has some filtering effect that makes it a bit more natural, or could make it a little bit more natural. And finally, expect it to take a lot of time. So the tuning of your parameters, the ranges of the parameters, but also what parameters do you expose to the user, what do you combine under one single knob, etc. So yeah. And finally, convincing people that physical modeling is actually cool and they should buy your plugins. That's a big challenge because a lot of people have expectations from physical modeling. So one comment that we had from a user is that they expected to emulate some physical instrument. And this is a fair assumption, but as we saw, we can also go beyond what is physically possible while still retaining these organic sounds. Other people who have seen physical modeling plugins expect to be able to open the model and play with all the parameters. So it should have more control. But yeah, maybe less is more sometimes for the masses. So yeah, generally people either love it or hate it. And this was at least the case for Atoms. We had someone calling it, unfortunately, it's a pile of dog crap. But on the other end of the spectrum, we had a user, a musician who made an entire album only using Atoms. So we're very, very proud of that. So yeah, in general, people really want MPE functionality with physical models. There's a lot of things you can control, especially if you have a bow or some physical model like that. You can link a lot of these parameters to the input parameters of your instrument. So yeah, that's a great thing. So yeah, to conclude, I showed you some challenges today on physical modeling, real-time physical modeling, and I'll just go over the main takeaways. So yeah, for implementation, first prototype before going real-time. Pre-calculate the coefficients and use the pointer switch to relieve some of the CPU in the guts of the calculation. Use slow changes, slow parameter changes, and do these outside of your scheme calculation to make sure that things don't blow up anyway. Spend time on making it sound good, and of course add a little bit of reverb. That always helps. And yeah, I think all I can say for point 5 is that have a great marketing team. I think Baby Audio really did a good job at marketing this product, so I'm really happy with their efforts. All right, that was it. There's some links here, so if you want to hear me talk more about Atoms with sound this time, there's a YouTube link here. Here's a GitHub link to my GitHub where there's some stuff that I also did during my PhD. And I guess most importantly, let's discuss on Discord later. So thank you very much.